Hello, chemists. This is Miss Placino, and you are watching screencast 4.3 on covalent bonding. Today we're going to talk about how to draw or represent covalent compounds or molecules with Lewis structures. This is a really important lesson. Everything else that we talk about this unit really is going to be based on your ability to draw Lewis structures for covalent compounds. So this is something you're going to want to get a lot of repetitions in with and a whole lot of practice so that this comes almost second nature. Let's take a look at the do now. Why do nonmetals share electrons instead of transferring them? Explain your answer using periodic trends. All right, pause the video, see if you can figure this out. Come up with a sentence or two explanation. So you can see I've drawn two Bohr models for fluorine. Both of these atoms have 7 electrons in their valence shell. We know that the main group elements, S and P block elements, are trying to complete their octets. In other words, trying to get 8 electrons in their valence shell. When metals and nonmetals react, metals have the same goal, but they're going to be able to achieve that by losing electrons. So metals can lose, the nonmetal will gain, and that's how we get an ionic bond. It's not going to work out as well by gaining and losing, or in other words, transferring electrons if you've got 2 nonmetals. If this fluorine atom tries to steal that fluorine atom's electron, it'll get to its 8, but now the other fluorine atom is even farther away from an octet and even less energetically stable, so that's not going to work. In terms of periodic trends, we know that fluorine as a nonmetallic element is going to be a really small atom. It's going to hold its electrons very close to the nucleus, and it's going to require a lot of energy to take away those electrons. Another way to think of that is that fluorine and other nonmetals have very high first ionization energies. So trying to take an electron away from a nonmetal is just going to be very energy intensive and not very practical. So we've got a compromise. Fluorine would like to gain an electron, but it's not going to happen when it bonds with another nonmetal. So instead, we're going to end up sharing this pair of electrons that I've kind of put an oval around. By sharing, now we've completed both fluorine atoms' octets, and that's going to lower the overall energy of those 2 atoms when they form the bond. Just to review some covalent bond background information that you probably have from the reading. Covalent bonds form between nonmetals only. For the sake of this unit, we're going to treat metalloids as though they are nonmetallic elements. They tend to bond, all of them, more covalently with other nonmetals than ionically. Any bond is going to be made up of at least 2 shared electrons. There is no such thing as a bond with just 1 electron. So in this case, we've got carbon, and its electrons are represented with the red. We know carbon has 4 valence electrons, so it would look like this. We know hydrogen has just 1 valence electron. Would look like the hydrogen with a little X above it. And in order to complete octets, or in the case of hydrogen, I guess it's more of a duet, its outermost shell is too small to hold 8. I'm going to share pairs of electrons. And generally speaking, when a bond forms, each atom involved in the bond is going to bring an electron to share. It's a special situation when one atom brings both pairs and the other atom is kind of just a freeloader, but we'll talk about that more later. If you're sharing 2 electrons between 2 atoms, that's called a single bond. If it turns out they're sharing 4 electrons between the 2 atoms, you have a double bond. And finally, if you've got 6 electrons between 2 atoms, you have a triple bond. Students always like to ask, is there such thing as a quadruple bond? And as far as I know at this point in time, no, there is no quadruple bond. We'll talk a little bit later this unit about how double and triple bonds form, and we'll just see that it's impossible to get a quadruple bond. For the time being, you can think about it as just too much electrons in too small of a space, and it's not going to work out. Okay, so a couple of lessons ago we talked about Lewis dot diagrams, and that's just when we take the symbol of the element and then based on the number of valence electrons it has, we put the dots around the outside of it. Those are going to be useful again in terms of covalent Lewis structures. We can look at the Lewis dot diagram, and based on how many paired and unpaired electrons that atom has, you can figure out how many bonds the atom wants to form. And of course, atoms don't want or anything like that. It's just going to be about lowering the overall energy, but we'll kind of personify the atom at this point in time. So it turns out that unpaired electrons that are all by themselves on a single side of the atom, are really reactive and they want to bond. On the other hand, if you have a pair of electrons on one side of the Lewis dot diagram, they're fairly non-reactive and tend not to get involved in bonding. So if we take a look at something like carbon, carbon has 4 valence electrons. We have 1 unpaired electron on each side of the carbon Lewis dot diagram. And it turns out that carbon wants to form 4 bonds. Go ahead and think about oxygen on your own. How many bonds does oxygen want to form? If you're thinking 2 bonds, you're absolutely correct. These pairs of electrons are not reactive. Again, in certain situations, we can force them to react, but generally speaking, they're not going to get involved in bonding. These 2 electrons, on the other hand, those are highly reactive, and they will form bonds. So let's try to draw a Lewis structure for a covalently bonded compound. So we're asked to draw the Lewis structure for CHCl3. One thing that you should do now that we know how to draw ionic compounds and we're learning how to draw covalent is you want to kind of size up the molecule and check, is this going to be ionically or covalently bonded? A really easy way to do that is just look and see, is there a metal? Carbon, hydrogen, and chlorine are the 3 different elements that are present in chloroform. All of them are nonmetallic, so it is a very safe bet that this is going to be a covalently bonded molecule. First thing we want to do is determine the total number of valence electrons that we have to work with. And if you think about it, you could just sketch out what the Lewis dot diagram is going to look like for each of those atoms. I know in CHCl3, I have 1 carbon atom. It has 4 valence electrons, so a total of 4 electrons from carbon. I've got a hydrogen with just 1 valence electron. And then I have 3 chlorine atoms, each with 7 valence electrons. This is essentially as hard as the math is going to get this unit. So that gives me 26 total electrons to play around with. It's worth noting that your valence electrons can move. They don't have to stay tethered to the element that brought them to the party, so to speak. But when it's all said and done and you double check your work, you want to make sure that you've accounted for all of the electrons. A lot of students get lazy and complacent and just simply don't want to take the time to do that. I cannot recommend enough that you actually go back and check your work. We'll talk more about that later. So we know how many valence electrons we have to work with. Up next is you want to determine which atom is going to be what I call the central atom. Basically, most of the structures that we're going to draw at this point in time are going to have an atom at the center, and then it's going to have other atoms sticking off of it. It's not too often that we're going to see something at this level of chemistry that I'm going to ask you to draw where you have multiple atoms with different atoms sticking off of them. It tends to be pretty straightforward and simple, and we're looking for what is the identity of that atom in the middle. The best way to do it is to look and think about which one of these atoms is going to be able to form the most number of bonds. If you look back at the Lewis structures that we just drew, hopefully you recognize that carbon, with its ability to form 4 bonds, is going to be our central atom. Next, you want to arrange the remaining atoms as symmetrically as possible around the central atom. So you can see that we've got our dots spread out symmetrically. I'm going to just start adding in the other atoms. So I know I have 1 hydrogen, and I'm trying to represent its electron with green. Carbons are in purple. Chlorine has 7 valence electrons in red. Same holds true for the other 2 chlorine atoms. If you've got spots where atoms are sharing 2 electrons or sharing a pair of electrons, replace them with a dash to represent a bond. So just to go back for a second, if I look, I know that electrons are being shared because they're occupying the space between 2 atoms. The ones that I've just circled, those pairs of electrons, those are being shared by carbon and hydrogen, carbon and chlorine. These, and I'll put like little boxes around them to try to make them slightly different. These are unshared. You can think of those electrons as belonging to that particular chlorine atom. They are not involved in bonding. So I'm going to change my structure so that instead of having dots, I've got dashes. Students will ask from time to time, well, these are really annoying to draw, these dots. Can I just replace them with a dash? And the answer is no. The convention is the dashes represent shared electrons and the dots represent electrons that belong specifically to an atom. So no, please don't draw dashes around the chlorine. Like, you wouldn't want to do this. Bonded to carbon, and then that. That is not the correct Lewis structure. You need to draw it this way. Finally, double check your work. There's two ways to do this. The first way is just to make sure that you've got all electrons accounted for. So I see 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. And that's the same number we came up with at the beginning. So that looks good. The other thing you want to look at is that you've completed the octets. There are some exceptions to that. We'll talk more later, but hydrogen is one of them. Hydrogen has a duet. Oh, 2 electrons around hydrogen. Great. 2, 4, 6, 8 around chlorine. 2, 4, 6, 8 around that chlorine. 2, 4, 6, 8 around that chlorine. 2, 4, 6, 8 around carbon. So octets, check out. Again, a lot of students choose not to double check their work, and they make kind of careless mistakes. The structures are going to become more complicated and more challenging as you get going. So it is really in your best interest to calculate the number of valence electrons you have to work with initially, and then to go through and double check your work at the end. So I've changed gears and I'm taking a look at practice problems. You're gonna, as you can see, have a whole lot of opportunities to practice with drawing these covalently bonded compounds. All right, so I have H2S. First thing I need to do is see how many valence electrons I'm working with. I have a hydrogen. Actually, I have 2 hydrogens and I have 1 sulfur present. So that gives me a total of 8 electrons. And maybe I'll just write that over here. I know that sulfur is going to be my central atom. Probably should have drawn that first. So let's erase that and kind of go through all the steps. Sulfur is going to be my central atom. I'm going to take my remaining atoms and arrange them as symmetrically as I can. And their electrons. Great. And then I'm going to replace the shared pairs of electrons. So the ones that have, in this case, the X and the dot, with a dash to show that they are being shared. Let's double check. I've got 2, 4, 6, 8 electrons, 8 of them around sulfur, 2 around each hydrogen. This checks out. Don't worry for the time being about shape, bonds are, and molecule is. I'm going to, actually, you should go ahead and pause the video. I'm going to work on solving these other 2 on my own. I suggest that you do the same, and we'll check in a minute. So I've gone through and I've drawn my 2 other Lewis structures, but I just want to talk about them real quick. I've drawn the dot diagram for both silicon and hydrogen. I've totaled up my valence electrons. I know I have 8 of them to work with. This is the structure that I've come up with, since I know silicon wants to form 4 bonds based on the number of valence electrons. 2, 4, 6, 8. I've completed octets. I've got 2 electrons around each hydrogen. I've got 8 around silicon. Coming over to NH3, we've got the valence, I should say the electron dot diagram for nitrogen with its 5 valence electrons, and for hydrogen again with its 1. That gives me a total of 8 electrons to work with. It's not always going to be 8, but that is a common number that shows up for small molecules. I've got the pair of electrons with nitrogen that is not going to form a bond. I want to make sure that I draw them. Then I've got the 3 unbonded or unpaired electrons that will react. So again, I've got 2, 4, 6, 8 electrons in total. I've completed the octet of nitrogen, and I've got the duet around hydrogen. I cannot even begin to stress how important those 2 electrons are. If they are missing, it's going to change a whole bunch of other things about this molecule. We haven't talked about shape or how to deal with molecule polarity just yet, but suffice it to say that it's going to change if you forget and you leave those valence electrons out. They have to be present. And this is part of the reason why you really want to go back through and check your work. It only takes an extra, I'll call it 10 seconds, and that's probably being generous, but it can save you a whole lot of headache and heartache down the road. We'll do some more practice with drawing Lewis structures for covalently bonded compounds, but first I want to talk about a couple of exceptions. It turns out that there are some elements that can, what we call, expand their octet. In other words, they're able to have more than 8 electrons in their valence shell. One such example is phosphorus. We know that phosphorus usually looks like this as far as this Lewis dot diagram is concerned. Essentially what can happen is phosphorus can split that pair of electrons if it needs to. And how will you know if it needs to? Well, usually phosphorus can only form the 3 bonds. You can think of it as being able to split that pair, and now it should be able to form 5 bonds. Maybe it looks something like that. If you go next door to sulfur, you get a very similar situation. Based on what we just talked about with phosphorus, try to make an educated guess on how many bonds sulfur would form, or can form, I should say, and what its new Lewis dot diagram might look like. If you're thinking something like this, you are correct. Sulfur can expand its octet, forming 6 bonds for a total of 12 electrons. We have some exceptions that kind of work in the other way as well. So phosphorus and sulfur can expand and hold more electrons than 8 in their valence shell. We already know about one element that holds less than 8 in its valence shell. That is hydrogen. So I guess it's not really an exception so much as it is just a reality. Hydrogen only has that first energy level, so it's not going to be able to hold any more than 2 electrons. The other one that I'd like you to be aware of is boron. Boron has just 3 valence electrons, so it's going to form only 3 bonds. For the record, if you are asked to draw Lewis dot diagrams for phosphorus or sulfur, these are the legitimate Lewis dot diagrams. Call them the correct Lewis dot diagrams. These are just pictures to help you visualize what's going on when the octet gets expanded. Oops, can't spell. They are not the same. If you're asked to draw them, please stick to the legitimate Lewis dot diagrams and not these, we'll call them artistic renditions of what the Lewis dot diagrams look like in the expanded octet. Let's do a quick example with those. I've starred the 3 problems that I would like you to try. So you've got pH3, PF5, and SF6. So let's just do pH3 first. We'll do that together. Phosphorus has 5 valence electrons. Hydrogen has 1. That's a total of 8 electrons. Phosphorus will be at the center. I know it's going to form 3 bonds to each of the hydrogens. So actually, very, very similar to the problem that we did before with NH3. And that should make sense. Phosphorus and nitrogen are in the same group of the periodic table. They're going to bond in a similar manner. Let's go next door to PF5. This is a case where phosphorus has to expand its octet. We've got fluorine with its 7 valence electrons, meaning it can only form 1 bond. And phosphorus, usually looks like that. It's got its 5 valence electrons, and we know in this case it's going to have to form 5 bonds. That's how you know whether or not the octet is going to expand. It needs to in pH3. It needs to in PF5. It does not need to, and therefore will not in pH3. So let's see, I've got 5 times 7 is 35 plus 5, so it gives me 40 electrons to keep track of. That's a lot. So I've got my phosphorus, 1, 2, 3, 4, 5. And exactly how you arrange the the fluorine atoms around the phosphorus, not too important at this point in time. Then you have to go through and add your dots. Do I really have to draw all those dots? Yes, you really have to draw all those dots. I can check for 40. I see 6 plus 6 is 12, 18, 24, 30, 32, 34, 36, 38, 40. I've completed all my octets. You do the same thing with SF6. Oops, you don't need that. Sulfur has 6 valence electrons. Fluorine, again, has its 7 valence electrons. 7 times 6 is 42, plus another 6 gives me 48 electrons that I have to work with. Sulfur is, of course, going to go at the center. I can put my 6 fluorine atoms around it, and then I can go crazy drawing dots. If you enjoy making dots, this lesson is right up your alley. All right, and that's all there is to it. It's the same general process. Go through and tally up how many valence electrons you have to work with. Draw your structure with the atom that can form the most bonds at the center, arrange things as symmetrically as possible, and double check your work. There's something called formal charge that you can end up having in covalent compounds. Usually you think of charge as being something. To get back to the lesson, there's something that you could have in covalently bonded molecules called formal charge. Basically what that means is there are situations where atom within a molecule can have a positive or negative charge. Let's take a look at ozone, O3. Just to keep up with that habit, I've got oxygen with its 6 valence electrons times 3. It's going to give me a total of 18 electrons. Now a lot of times when people draw this structure, they end up making like a triangle of oxygens. This actually won't form. I know you can draw a Lewis structure where it does form, but these triangles are very, very high energy and they tend to just unravel. So you don't see triangles very much in chemistry at all. So you've got to try to do this a different way. You can still kind of get things set up in that triangular format, but instead of going through and connecting all of them together, we're going to have to try to divide up the electrons a different way. So let's bond them, and we'll give one of them a double bond. And you might be saying, well, wait a second, oxygen usually only wants to have 2. You've given it 3. Aren't you breaking rules? And in this case, I mean, in a way, yes, we are breaking rules. But ultimately, what we want to do is complete octets. So we'll go through and we'll fill octets. So I've got 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons present. They're all taken care of. If an atom has more bonds than it typically wants to have, we give it a positive charge. You can think about it as a pair of electrons that used to belong solely to that atom is now being shared between multiple atoms. So it's going to have less electrons around it, so it's going to therefore have a positive charge. In this case, which of our 3 oxygen atoms should have the positive charge? Hopefully you're thinking the one at the top. Usually oxygen likes to form 2 bonds. We've given this oxygen at the top a total of 3. It's oversharing, so it therefore has a positive formal charge. Atoms that have less bonds than it typically wants get a negative charge. You can think about it as, okay, this atom is used to sharing the pair of electrons. Now those electrons belong only to that atom. That extra pair of electron ownership is going to make it negative. So if we go back to our picture of ozone, which of the remaining 2 do you think has the negative charge? Hopefully you're thinking, well, it's got to be the one on the right, because this oxygen over here has exactly what it wants. 2 bonded pairs of electrons and 2 unbonded, unshared pairs of electrons. The goal should be when you're drawing a Lewis structure is to try to minimize the number of atoms that have formal charges. This is fairly unstable to have formal charges. It kind of happens from time to time. It's not the end of the world, but the overwhelming majority of the molecules I ask you to draw are not going to have a formal charge. Try to minimize that. And worst case scenario, if you can't go through and give the atom exactly how many bonds it wants, at least give it an octet. You know that all atoms, minus the exceptions we talked about, are always trying to get 8 electrons in their valence shell. So if you can't give it the perfect number of bonds, at least make sure it has 8 electrons in its valence shell. We're going to wrap up with a concept known as resonance. And resonance just kind of exists when you've got molecules that can be represented by multiple structures. Really, the arrangement of the atoms stays exactly the same, but the way the atoms are bonded to each other, for example, are they all single bonded or double bonded or triple bonded, that sort of thing changes. These are called resonance structures. So the ozone molecule that we just talked about is an example of a resonance structure. I could take this pair of electrons and I could move them in between these 2 oxygen atoms. That would cause one of these shared pairs of electrons to move. I can go vice versa. You get a resonance structure. Let's erase those as well. One of the most famous examples of this, those of you who are thinking about taking the SAT-2 in chemistry, benzene is a really good example of another molecule that exhibits resonance. We can take those double bonds and essentially just kind of swap them all over. So they're now in between 2 different carbons. and you end up with benzene again, a slightly different form of it from a picture perspective, but it's the same exact molecule. So we can see that the arrangement of the atoms has not changed, but the way they're bonded together, the locations of the single and double bonds, has changed. So just to wrap up, I want to get back into the practice problem section. And I know I showed you before, and you can see it in your workbook, you have a plethora of problems to work on. It's really important that you keep practicing with it. If you want to skip out on drawing the little Lewis dot diagrams because we worked with those enough and you feel very comfortable with them, by all means, go ahead. But I cannot stress how important it is to get your total electron count, especially as molecules become more complicated, or sometimes you're even drawing ions, and to go through and double check your work. Make sure that you have the same number of valence electrons present in the structure that you calculated based on the formula. All right, that wraps it up for today. Sorry this one is a little bit long, but like I said, this is a super important lesson, and we're going to be building on it in future lessons. Thanks for tuning in, and I hope this was helpful.